Good morning, everyone. This is Penny from Wisconsin Land and Water, and I'm their Conservation Training and Membership Services Manager. And today, our webinar is going to be on prioritizing contaminants in natural waters. And our presenter is Steve Corsi. And Steve is a research hydrologist from the U.S. Geological Survey. So we're happy to have you join us. And I think it's time for Steve to take over.
Okay, thanks, Penny. You hear me okay?
I can hear you. Go ahead. Thank you.
Great. Great, thanks for the opportunity to speak with all of you folks. Glad to get the word out on some of the work we've been doing and glad that there's some interest. So I'm Steve Corsi. I've been a research hydrologist with USGS since 1988. I am in the Middleton office in the Upper Midwest Water Science Center. So in the past, I've worked primarily on water quality issues since I started, and in recent years, I've really focused in on what's commonly called contaminants of emerging concern, which doesn't necessarily mean these contaminants are just emerging, but they may have been there for a long time, and we're just beginning to understand some of their potential ecological effects. And that's really what I'll be talking to you about today. I'll be focusing in on three different primary topics: microplastics as the first section, polycyclic aromatic hydrocarbons, or PAHs, as the second topic, and then general organic contaminants as a third topic, which will include a number of different things, including contaminant classes like pesticides and flame retardants and pharmaceutical compounds. So with that, we'll get right to it. We'll start with microplastics. So we've worked with the Great Lakes Restoration Initiative through EPA and with the Milwaukee Metropolitan Sewerage District on some microplastics issues. Currently, we've done 3 different studies, and I'll kind of summarize those 3 studies. They build upon each other and kind of complement one after the other, learning something new each time, and I'll kind of go through that. So just to give you a quick introduction, microplastics are plastic particles less than 5 millimeters in diameter. And there's many different sources of microplastic particles, things like the fibers that come off of our clothing or other textiles. There are things like breakdown products. So many of these solid plastic products will end up in the environment and eventually break down into small fragments that are categorized then as microplastics. There's a lot of different products like styrofoam that break down into small beads or particles. And then there's sometimes there are spills of pre-production pellets, for instance, that are used in the manufacturing process but somehow get away from them. Those are more common than you might think, actually. And then plastic bags, pretty common for us to see plastic bags around the environment. Well, they eventually break down into small films that are categorized as microplastics as well. And then the sewage treatment process doesn't really handle plastic particles. And so at times, sludge is spread on the land surface for fertilizer, and microplastics can enter the environment through that avenue as well. So to date, there's been quite a few studies. This is kind of a young science, really. 10, 15 years ago, you really wouldn't hear much about microplastics, and now you hear about it all the time. People have now done studies all over the world, and pretty much every study finds microplastics, no matter where they're studying, from the Arctic to the Antarctic, at the water surface, at the subsurface, in the sediment, in the coastlines, and freshwater. environments and lakes and rivers around the globe have found microplastics in groundwater, believe it or not, in drinking water, in our tap water, people have found microplastics in marine and freshwater organisms alike, and in humans. And so even in our daily consumer products like salt, sugar, honey, bottled water, and then something that always hits home for people in Wisconsin for some reason is they found it in beer as well. So why should we care that microplastics are in our environment? Well, the research, like I said, is young, but still there's a whole lot of activity going on right now. And so to date, there are more than 100 species where people have done studies and found microplastics to be present in different organisms. They've been found, for instance, something local in 82% of Lake Superior lake herring from a study in 2013. In mussels in Nova Scotia, they find 126 to 178 microplastics particles per organism, and those are pretty small organisms. They think about over 100 plastic particles just in one mussel. So with the presence of microplastics in organisms, there's a bioaccumulation or a trophic transfer up the food chain. As larger organisms consume smaller organisms, the plastics stay with them and basically get bioaccumulated. The hazards for presence of microplastics in organisms are not super well understood yet. There's a number of studies that have been done and a lot going on right now. To date, some of the things that stand out in oysters, for instance, when they're exposed to microplastics, there's reductions in their reproduction, and their offspring are slower growing, and there are fewer offspring when they're exposed to microplastics. It can obstruct the digestive system depending on what kind of microplastics they consume, so it can ultimately end up as nutritional deprivation. And they can also migrate into the circulatory system and can reduce the immune response and can ultimately result in mortality. Some organisms are just able to pass some sizes and shapes of microplastics and there's no effect. Other organisms and other types of microplastics can have an effect. So it's not just a yes or no answer to that question. So in the Great Lakes area, there have been a number of studies done from academic researchers in the past that have quantified microplastics in samples by skimming the surface of the lake. And so in Lake Superior, for instance, 37,000 particles per kilometer squared is the average concentration they found in some recent studies. In Lake Michigan has been well sampled, and this is the average for that. Huron, the concentration looks to be lower, but then again, there's only a handful of samples. It's really not well studied in Lake Huron, as opposed to Superior, Michigan, Erie, and Ontario, which have had quite a few samples collected. The one thing that's really that really stands out is 230,000 particles per kilometer squared in Lake Ontario. So we do see that as you get to the end of the Great Lakes system before it enters the St. Lawrence, that's where we see our highest concentration. So through the kind of industrial zone in Lake Erie and Ontario, it's picking up a fair amount of plastic particles. And so our first study was on Great Lakes tributaries, and this was a study with the Great Lakes Restoration Initiative. Back in 2014, we did the sampling, and there's a paper published in 2016, if you look for it. Austin Baldwin is the lead author. And So we sampled 29 Great Lakes tributaries. Overall, we collected 107 samples. We have a few samples in each of those tributaries, trying to spread those out under different hydrologic conditions, so high flow and low flow. And in those samples, we found microplastics in each and every one, no matter where we sampled. So that's a significant result in itself. The fibers, those particles that come from things like clothing or possibly some type of insulation, has fibers, things like that. Those were the dominant plastic type in our samples. And that's different than what they found in the lake surface samples. I'll get to that in the next slide. But there's a big gap in the particles that were found in rivers versus lakes, and so we had to explore what is making that, what's the cause of that difference. So many plastic types that were found were correlated with urban land use. Fragments, films, microbeads, and foams were correlated with urban land use, and they were also correlated with rain and snowmelt runoff. But then when we looked at the fibers, we found that they were present in all land uses, not just with urban land use, but they were also not correlated with hydrology or wastewater effluent. So that was a little bit of a surprise and tells us that fibers are basically spread over the land surface and are present under many different conditions. There isn't one specific thing driving the presence of fibers. So on your left, we see basically a stacked bar chart that gives us an indication of the proportion of the types of particles that were found in lake samples from all those different lake studies. And on the right is the tributary study that we conducted. So the big difference here is, fragments were the largest source in the lake studies, whereas fibers were more abundant in the river studies. And so we wondered, the tributaries are the source of microplastics, at least one of the sources of microplastics to the lake. So why is there such a difference? So looking a little further, we decided that density was important to look at to determine whether these will settle out, because the sampling done in the lake is all done on the surface. And in the tributaries, we also did it on the surface, but tributaries have a little better chance of things being well mixed. So the turbulence in a river will keep even heavy particles mixed into the water column. So some of the densities will show basically that the foams are much less than the density of water, which is 1. Some of the polyethylene and polypropylene are also less than the density of water. But then we get the neutral buoyancy, and so some of these fragments are also heavier than water, but most of the fibers are heavier than water. And so our hypothesis was that the fibers and some of the fragments would be settling out possibly through the water column and into the sediments of the lakes. And so we set out to validate or verify that hypothesis, starting off with a study in the Milwaukee River Basin. And so this is our study with the Milwaukee Metropolitan Sewerage District. And so there's a few sites here that that were influenced, or that were in deeper waters in the estuary. So these basically downstream sites, and then also at the outer harbor and out into the lake. And for those, we were able to sample through the water column, not just at the surface. They were deep enough that it made sense to sample through the water column. And so we had a sampling system like this set up, where we sampled the surface like traditionally, and then we had several nets that we dragged through the water column at different depths to determine what the microplastic concentrations were there. We also sampled sediment as well. And getting past all the nitty-gritty from this particular study, we found that for polymers that had a density below 1.1 grams per centimeter cubed, we found that they were most abundant at the water surface, less underneath the water surface, and even less in the sediment. And then polymers with density greater than 1.1 had the opposite effect. So it's what you would expect. If they're denser than water, you're going to find that they settle out through the water surface and into the sediment more. And then also the orange color is the fibers, and so that really does tell us that we're starting to answer that question: why is there such a difference from fibers comparing the lakes and the river samples? Is that most of the fibers are either suspended in the water column below the surface or in the sediment. And then we sampled the sediment of Lake Michigan and Lake Erie as well. And again, this orange color is the fibers, and you can see that all throughout the sampling, fibers dominated the signal. Most of the particles that we found in the sediment of the Great Lakes, these two Great Lakes, were fibers. There's a few other particles that we did find as well, but definitely the higher density particles are what we're finding in the sediment, but really dominated by that, by those fibers. So that kind of closed the loop on the question of where did the fibers go, and we can kind of move on from that onto other studies. But let me just touch on what can be done about microplastics contamination. So first off, I know you folks are focused on management of different water resources, and so this may be important to consider. There's two primary things that we consider: is reducing at the source or reducing before it hits the stream. So many places have banned certain types of plastic products. Plastic bags have been banned in New York, California, and Hawaii. Several different countries have banned plastic bags entirely. Plastic straws have been banned by some areas, and then other types of bans like polystyrene or styrofoam food containers, utensils, plastic stirrers, water bottles, things like that. That's a tough thing to do, and kind of in society, there's a lot of resistance to that type of thing because it does add a whole lot of convenience to our life. So it's tough to manage this way. In fact, one country in the world now has banned all single-use plastics beginning this year and kind of moving through 2020. China has done that, and so that will make a big difference supposedly in their country, but really we don't know how much impact these bans are going to make. That study hasn't been done, and really I would expect it to take quite a long time to see that difference, because plastics have been in our world for so many years that banning it 1 year isn't going to be cleaning it up by the next year or so. I would expect 10 to 20 years before you see the full impact of some of these bans. The other thing that can be done then, something that's commonly done in urban areas, is stormwater management and agricultural areas. So stormwater management practices like infiltration basins or green infrastructure, like you'll see the picture on the right, this is basically an infiltration basin coming off of this parking lot. So a lot of the plastic particles would be captured in the infiltration basin before it gets to a stream. Settling basins or detention ponds. Some detention ponds will, or I should say some particles will be captured by detention ponds, but some of these particles are buoyant, and so it'll handle a portion of the particles, but not all. And then there are some stormwater filtration systems, and all of these are yet to be tested for how effective are they in reducing microplastic particles getting to the stream or lake. So that's what I have on microplastics for now, and I'll pause shortly for any questions on microplastics before I move on to the next topic.
So please feel free to either unmute yourself and ask a question or send it through the chat line. We're taking them now and throughout the presentation.
Steve, you said in Michigan there was one area that had a much higher microplastics source than I saw in other lakes. Was that explained by some industrial source, or do you have any idea? Was that Michigan 107?
Right, Michigan 107, and I'm looking at that. In my memory, I'm thinking that's the Grand River. So that's a good question. I haven't looked into the exact source of that, but there's a lot of different influences in the Grand River in Michigan. It's one of the largest watersheds in the Great Lakes Basin. And there's a fair bit of urban influence upstream. There's a lot of agriculture influence as well. And as I mentioned, that the fiber particles did not have a dominant source. So from both agriculture and urban land uses, we can see contributions from fiber. So it's hard to tell just from the information that we have there what the actual source is. Good question, though. That's an avenue of research that we'd like to pursue, and we have kind of a proposal to start doing that in urban areas to quantify different source areas and what the contribution is from, let's say, parking lots and roadways versus residential areas and such.
Yeah, it looks like Erie 109 is another one that's a heavy hitter. So yeah, it'd be interesting.
No doubt. And Erie 109 probably isn't a big surprise, since that's got input from basically the Detroit River coming through. So a large urban area here, and then Toledo to the west of that. And so, and then there's a ton of agriculture. The Maumee River Basin drains here. The Raisin River, the Clinton and Rouge, the Huron River are all draining right there. So it's kind of a focus area for a lot of different sources. All right. Any other questions on microplastics? Okay, thanks. So I'll move on to primary sources of PAHs, or polycyclic aromatic hydrocarbons. We use the multiple lines of evidence approach to try and track down what are the sources of PAHs and help people understand how they might be managed for reduction of concentrations in sediments and water. There's a ton of people who have been involved in both of these studies, actually. I've been, including contributors here. So throughout this whole presentation, we have federal agencies like Fish and Wildlife, EPA, Corps of Engineers, NOAA, and then local agencies like Milwaukee Met, and then there's some academic institutions this particular one, University of Helsinki. Some of the other work, we collaborate with St. Cloud State University as well. So all of this stuff is really a very collaborative effort. We'll start with a little bit on sources. What are PAHs? They're chemical compounds that form through combustion of organic material. So wood burning, coal combustion, diesel exhaust, used motor oil, gasoline exhaust, and then there are things like tire particles from tire wear. Asphalt has some PAHs, and then the sealants that people use on pavement, asphalt-based or coal tar-based sealants, and creosote-treated wood. So now let's take a quick look at relative concentrations from these sources. You can see that wood combustion is pretty low comparatively, so is coal combustion. And then it kind of goes up from there. And really the largest concentrations come when we get to the bottom row here. Asphalt-based sealant higher than others, not super high, but coal tar-based sealants are getting quite high, as well as creosote-treated wood. And we'll get through an analysis here that kind of gives us a feel for what we think are the largest contributors in sediments throughout the Great Lakes. So why do we care about PAHs? Well, PAHs do pose a human health hazard. There's exposures from a number of sources, and the one we have here, the example we have here is from coal tar sealant and how it's tracked into your home and ends up in the dust in your home and such. But there are other exposure mechanisms as well. There is an increase in cancer risk that's been shown from exposure to PAHs. And certainly there is a hazard to aquatic life as well. There's many detrimental effects that have been documented in different aquatic organisms, fish, aquatic insects, frogs, salamanders, newts, and such. And the literature is kind of filled with information on that. So it's definitely something to be concerned about if we're seeing a lot of them in our waterways. So in Great Lakes studies that we've worked on or collaborated on, or some of our partners have worked on through the Great Lakes Restoration Initiative, we found that it's present in many different compartments. Water samples we've collected in all 57 tributaries that we sampled. We had detections with PAHs. In 20 of those 57, we found concentrations exceeding water quality benchmarks. And sediment samples throughout the Great Lakes, we've sampled over 70 different sites, and we see PAHs in nearly every sample, and it's commonly observed above sediment quality criteria concentrations. In mussels, the NOAA Mussel Watch program has found PAHs widely in mussels monitored throughout the Great Lakes in harbors, nearshore, and offshore environments. And the USGS office in our office in La Crosse has studied tree swallows and the emergent insects that they consume, and they were contaminated with PAHs on a regular basis. And it's likely that many other species that ingest insects around the waterways would also be exposed to PAHs. And certainly fish. Fish consume many of these insects as well, and plus they're exposed to the water, the sediment in the water, and in many cases symptoms known to be caused by PAHs were regularly observed in Great Lakes fish samples, including largemouth and smallmouth bass, brown bullhead, white sucker, and fathead minnows. And those are just the ones that have been studied. So here's just a comparison of So we've done 2 studies on PAHs. One, our first one, which is published now, was in Milwaukee, and we sampled 40 different streams, sediments in 40 different streams in the Milwaukee area. And this is a comparison of concentrations found in large urban centers around the world where they've done similar studies sampling stream sediment. So in Sydney, Australia, they have concentrations mostly below 10 milligrams per kilogram, between 10 and 20 maybe in Bangkok, Thailand, in Beijing, somewhere similar, and in Delhi, India, it's a little bit higher, but usually below 25. And these are pretty highly urban areas with pretty large population densities where you'd expect to see contamination from PAHs. And so these are the results from Milwaukee. Concentrations up to 200 milligrams per kilogram with a median around 50. And so it's kind of striking to see this difference, and noting that 78% of the samples had concentrations that were likely to cause adverse biological effects. So there's something different in Milwaukee than there is in these other highly urban areas. And one of the objectives here was to determine what that was. So we went through multiple different analyses, establishing multiple lines of evidence to try and determine what is the source of these PAHs in Milwaukee stream sediments. So there are 7 different analyses techniques that we used, all giving information on what could be the primary source. Each and every one of them did not rule out coal tar seal coat, and some of them pointed directly at coal tar seal coat. And so the common conclusion that we have compared to other studies in other areas of the U.S. is that coal tar sealants are the primary source of PAH contamination in urban stream sediments. And so for this particular study, we found that 77% of the total PAH loading in the sediments that we sampled was from coal tar sealant dust. And we did a similar study around the Great Lakes region more recently in 2017. And so the numbers within here are how many sites in each watershed. So there's 4 sites in the Fox River watershed, 12 in the Milwaukee River watershed. This is the St. Louis, the Bad River, the Manitowoc River, and the Kinnickinnic River and the Root River system. So those are the ones you may be familiar with in the Wisconsin area, but then throughout the Great Lakes as well. And we largely found that, well, let me take a step back here. So this is the land use in those 70 watersheds or 70 stream sites that we sampled. So we really wanted to focus on getting a good gradient of urban, non-urban land use. So it goes from basically zero, almost zero urban land use up to 100% urban land use. And this is an example of the type of analysis that we do. So this is a chemical fingerprint from different PAH compounds. There's 12 different PAH compounds represented here. And this is the relative concentration, so the percent of total PAHs for each of these. And you can see that each of them has kind of a unique fingerprint. And so we've done this for not just these 6 different sources, but many different sources. And then we superimpose the fingerprint from the average concentration in the Great Lakes. And it's pretty easy to pick out which is the best match here. It's almost a perfect match, except a little bit of difference here in a couple of the compounds for the coal tar sealed pavement dust. And so that's one of the ways we look at our data to determine at each individual site what's the primary source. And we have some statistical metrics that we can calculate to determine what is the closest match, which source is the closest match. That's one of the 7 ways that we've evaluated this. And now for the Great Lakes sites, so these are all the Great Lakes sites, and they are sorted from lowest to highest PAH concentration here. And then we looked at each of our lines of evidence, and then in the end we have a summary saying, okay, now how many of them are a specific source, and is there a consensus that it's one source, or is there a majority that it's one source? So when there's a check mark, it means every one of the lines of evidence points to the same source. Otherwise, if it's just mentioned, that means the majority is from one source. And if you look at it, the CTD is coal tar dust, and 7 means that we have 7 samples that have been collected over the U.S., basically vacuuming the dust off of a surface that had coal tar pavement sealer on it. And so 35 of the sites were a consensus that coal tar dust was the source. 22 sites were the majority of coal tar sealants, and 5 sites were vehicle related. Those are mostly on the low end of the concentration range. So the higher concentration range mostly were from coal tar dust. And then 8 sites where we didn't find that there was a majority and couldn't determine what's the major source. So basically what we're finding is 80% of sites had the primary source pointed at coal tar dust. And this is a pretty well-established issue now. It was first found in 2005 in Austin, Texas. They have since banned coal tar sealants in Austin. There have been a number of studies done now, again, similar to what we've done. They've done some what we call source apportionment, where they're trying to determine what's the major source in sediment samples. It's been related to an increase in PAH exposure in children. And it's also been related to toxicity in freshwater organisms. And then in Minnesota, they sampled a number of different detention ponds, sediment in detention ponds, and found it to be the major source there as well. And since then, Minnesota, the entire state, has banned the use of coal tar sealant. It has been related to higher concentrations in dust within your homes. So coal tar sealants in parking lots or driveways basically led to a higher concentration in dust within your home. And so that gives you an indication that there's probably an increase in exposure to humans. And then there have been publications now on what are the implications for the environment, what are the implications for human health, and what can you do as far as stormwater management. So that could be important for people who are involved in water resource management. And then last, the Austin area banned it in 2006. And in 2014, our colleagues in USGS down in Texas did a study in Lady Bird Lake, which is within Austin, and looked at the sediments and how they've, over time, and how concentrations of PAHs have been reduced since the ban. So it is pretty apparent that this ban, in fact, has made a difference. So In Wisconsin, 18 communities now have banned high pH seal coat, including Milwaukee, Green Bay most recently, Sheboygan, Manitowoc, Dane County, multiple other communities in the Milwaukee area. I have heard that Wisconsin legislature is considering a ban statewide now. I'm not sure where that's at. And the other option is reducing before it hits the stream. Similar to microplastics, you can use stormwater management practices. So infiltration basins, green infrastructure, settling basins, stormwater filtration systems, all would likely be effective at reducing PAH concentrations because PAHs are commonly bound to sediments. And so settling out sediments or filtering out sediments will likely be effective at reducing PAH concentrations. But really haven't done a whole lot of testing for effectiveness. Most of the BMP testing or stormwater management testing has been done on things like suspended solids and nutrients and such, and not a whole lot on PAHs. So I'll pause there and give you a chance to ask question on PAHs, if there are any questions.
Steve, a question came in earlier. I think it was when Donalea asking the question. It said, what's happening at ER 109 too? Do you want to take that now, or you want to do that at the end of your presentation?
That was from microplastics.
I don't know. Steve replying right now, I think. It's Steve Kircher out there has got a question.
Okay. I think that was the microplastics one. So
you see it in the, it says, what are alternatives to coal tar sealants? If.
Yeah. I see that one from Steve. Yep. So there's a number of different alternatives out there. I'm not an expert in alternatives, but I do know that asphalt-based coal tars or asphalt-based sealants are much lower in pH concentrations than coal tar sealants. There's several other alternatives out there and resources online to find those. That's a question that has been posed to the MMSD, and they were looking into options. And I think an organization called Clean Wisconsin has been looking into alternatives as well. So yes, there's definitely alternatives out there, similar in cost and effectiveness to coal tar sealants. Any other questions on PAHs? Okay, we'll move on to general trace organic chemicals in Great Lakes tributaries. So again, this one is a large collaboration with many different folks, and it's through primarily the Great Lakes Restoration Initiative. So you may have heard a fair bit about different organic chemicals in the past, and maybe it gets a little overwhelming because now people are monitoring for hundreds of different chemicals per sample. It's not uncommon. There's been studies now throughout the US where they have over 700 chemicals that they're analyzing per sample. They look at occurrence and concentration of these different chemicals, and with improved analytical techniques now, the detection is down in the low nanogram per liter levels, which is super low. It's difficult to understand what's really important in all that. So if you have, out of those 700 some, 400 and some of them were detected, which ones really matter? Which ones should we care about? Which ones will have biological effects? And so things like pesticides, pharmaceutical compounds, personal care products, flame retardants. PAHs are in this category, dyes and flavors and fragrances sometimes show up. So which ones are biologically relevant? Which sites are they relevant at? And so we look at typically a couple different ways to evaluate these using water quality guidelines or a database from EPA called ToxCast that has information on chemical potency. So I'm going to give you a few examples of the studies that we've done through the Great Lakes Restoration Initiative, and then in the end give you a summary of chemicals we found to be high priority using these evaluation techniques. So for starters, the first study through the Great Lakes Restoration Initiative began in 2010, went through 2013. We sampled 57 tributaries, which represent about 70% of the flow from the US side of the Great Lakes. There's a wide range in land use from urban to agricultural. We monitored for 66 different compounds, and they represent 15 different chemical classes, including pesticides, PAHs, non-prescription drugs, flame retardants, and several others. We collected over 700 samples for this study throughout different seasons and hydrologic conditions. So that's study number one. And study number two was, in fact, based on results from study number one, we found that there were some pesticides that were of concern. So we expanded our pesticide list that we were analyzing for and focused in on 16 different Great Lakes tributaries and sampled monthly from 2015 to 2016. So 233 different compounds at 16 tributaries with a range of different land uses. Again, we analyzed for herbicides, insecticides, and fungicides, including the active ingredients and their degradation products. Okay, so that was study number two. Study number three I already showed you was the PAH study. So this is study number four, pharmaceuticals. So there's pharmaceutical compounds came up in our first study as well. And so we expanded on that from November 2017 to July 2018. We ended up sampling 44 tributary sites for pharmaceutical compounds. Again, a wide range in different types of land use. And from no wastewater effluent up to 28% wastewater effluent as flow in the stream. And we collected 107 water samples for this study, again, throughout different seasons and hydrologic conditions. We're shooting to get more than 200 compounds analyzed. 111 of them have been reported so far, so we can talk a little bit about results from those 111 compounds that have been reported. And just to give you a feel for some of the things we see here, these are the sites where we sampled. Here, these are the watersheds on the top. This is just the number of compounds that were detected in any given site. So of the sites we sampled in the Milwaukee River watershed, Milwaukee River at the mouth, that's right there near Jones Island. About 35 compounds were detected. In the Clinton River, we detected up to 44 compounds at one site. And it kind of gets a little bit overwhelming thinking about all these different compounds that are detected at these different sites. In fact, there's 23 sites that had more than 25 pharmaceutical compounds detected. And so how to handle that and how to break that down into something that's digestible and usable for the pharmaceutical compounds that are really biologically active and may matter. So then our, I guess the fifth study here, We sampled using passive samplers, which are basically a way to sample simulating uptake by biological organisms. We use these membranes that simulate biological uptake. So they should be very relevant as far as what chemicals could the organisms be exposed to. Sampled 70 Great Lakes tributaries, analyzed for 187 different compounds and detected 144 of them in the samples. So this included things like organochlorine pesticides. Those are pesticides that have been banned. PAHs, wastewater indicators, pharmaceuticals, flame retardants, BCBs, and others. Okay, so all of that's a whole lot to digest, right? There's over 500, I think it was almost 600 chemicals through all those different studies that we monitored for. And so we're not going to get into detail for all those, obviously. I'm going to, what we did was prioritize these chemicals based on which ones were biologically relevant, not just using concentrations or detection alone, but using the potency of each chemical to help prioritize which ones really matter for human health and for ecological health.
Okay.
And
So,
we also,
to me, that's all good.
was there a question? Okay. And so we also use that to help us prioritize at which sites these chemicals are present at concentrations that are biologically relevant. Included in that is an evaluation of chemical mixtures. So which sites is the potency of certain chemicals actually increased by the occurrence of additional chemicals? And so to do this, we're using concentrations, chemical mixtures, and potency of all these different chemicals and how they might be related to each other. And then we can go as far as predicting what the adverse outcomes are that we might expect. Like, for instance, would fish have reproductive issues? Would they find tumors? Would they have liver disease? Something like this. So some of the information that we have gathered from EPA toxicology databases can give us some of that information to assess these chemicals. And so we use three primary methods, just occurrence and magnitude, like I mentioned, but that really only gives you a chance to rank by highest to lowest concentrations and frequency of occurrence, and it doesn't take potency into account. The water quality guidelines or benchmarks or criteria, whatever you'd like to call them, things from, for instance, water quality guidelines from EPA or Wisconsin DNR are commonly used here. From some chemicals. So we compare our concentrations basically using a toxicity quotient, which is a simple concept. We take the observed concentration divided by the concentration benchmark. So that tells us, do we have exceedances of our concentration benchmarks or concentrations of concern. And then using another database called ToxCast that has information on quite a few more chemicals than we could find using established water quality guidelines. We can go a bit further and determine something similar. It's called an exposure activity ratio, but we take the observed concentration and again divide by the concentration of concern from that database. So it's basically the same concept, different water quality evaluation. And with that, we can evaluate potential biological pathways like I described before. Does it influence reproduction, or does it have potential for tumor development, that type of thing. And so through all of that, I'm going to get to the point here and show of all those about 600 chemicals we've evaluated, these are the ones that have kind of risen to the top as far as potential for adverse effects. And this table includes the chemical use class, so what are these chemicals used for, and then the actual chemical name. The number out in front is how many chemicals from that chemical use class. So we can see there's a triclosan, which is antimicrobial, some detergent metabolites, some flame retardants, phosphate-based flame retardants. 5 of those show up. 2 flavors and fragrances show up as having potential adverse effects. Fungicide, herbicides, some hormones, a few insecticides, and PAHs. That's not a surprise. 9 different PAHs show up as having potential adverse effects. And we kind of saw that in a little more detail previously. Some components of plastic like BPA, DEHP, and triethyl citrate. And then 14 different pharmaceutical and personal care products have shown potential for adverse effects as well. And so that's kind of where we're at now. And really, some of these studies aren't complete yet. We're going through the data. Like I said, some of the results have not yet been reported, but we've been kind of evaluating them as they come in. And this is kind of an example of how we do it by site. So that passive sampler result, where we had 187 chemicals that we monitored, kind of put them in, organize them by each different Great Lake, the tributaries from the Great Lakes, and then order them counterclockwise. So, for instance, Lake Michigan starts up at the Manistee River, goes around down into the Chicago River, and then back up the eastern coast. And you can see that the urban areas, once you hit Green Bay, Manitowoc, Sheboygan, this is the Chicago area. These numbers are the sum of the exposure activity ratios, in other words, potential for adverse effects. And so that potential gets greater in these urban areas. And then there's some certainly agricultural areas here as well, the Kalamazoo, the Grand River, Muskegon. And then in Western Lake Erie, we see potential for adverse effects as well. Western Lake Erie is pretty well known for some contamination issues in many different ways. And, there's no exception here with the contaminants of emerging concern. So we've done some land use analysis on all of these as well. So where are there potential for adverse effects, for instance, from insecticides? And it's more likely to be urban areas than other areas, and crops or pasture and hay. For herbicides, there's correlations between adverse effects from these chemicals for all 3 of these different land uses. Fire retardants, it's mostly urban and crops. And then detergent metabolites is primarily urban. Pharmaceuticals surprisingly showed up with correlations between all 3 of these land uses as well, which kind of really gets the mind spinning. Where could that be coming from? You know, we certainly don't have an answer. You know, there's possibilities that it could be from in these ag areas from septic leaking and such, or some of the pharmaceuticals. I haven't looked in detail yet. That's a study we're working on. Some of the chemicals may be also used in agricultural applications. So then PAHs and wastewater indicators are certainly correlated to urban land use. So now, again, we go back to how can these be managed? And that's going to be on a case-by-case basis. These are pretty different chemicals. A lot of these have different chemical properties that need to be considered if you want to understand how to reduce the presence of these chemicals. Obviously, the PAHs and coal tar sealants we've talked about, pharmaceutical compounds, Could be wastewater effluent or leaking infrastructure. So, the sources are important to understand before you think about management practices. Pesticides from non-point runoff, wherever they're applied, fire retardants and plastic components, probably more likely to be from non-point runoff as well. And so what do you do to control them? Again, there's the possibility of reduction at the source, which would be different depending on what contaminant you're talking about. Reduction before it hits the stream, again, would be things like improved wastewater treatment, which is an active area of research, like how do they, because originally wastewater treatment plants were not designed to handle these types of chemicals. So they aren't really expected to treat them well. And so there's a lot of research being done to understand how can wastewater treatment plants change their operations so that less of these organic compounds get released into the environment. That's a pretty expensive undertaking. And then there's urban and agricultural runoff management. There's a lot of different options for that, depending on what chemical we're talking about. But considering whether it's a dissolved or particulate form of a chemical will allow you to design different approaches to reduce presence of different chemicals. So I think that's what I have for you today, and I'm happy to take a few more questions.
There's a couple in the chat box. Can you look at those, or would you like me to read them?
Let's see. So Steve Keith is asking for preliminary screening of an effluent for compounds of concern. Are there indicator parameters that could be tested in an initial round before testing the broader list? That's a great question, Steve. We commonly use the study number 1 that I mentioned with 66 compounds. It's got 15 different classes of chemicals. That's what we use as our initial screening schedule or analytical schedule. So that has things like pesticides, it's got PAHs, it's got flame retardants, it's got different pharmaceutical compounds, different plastics components, things like that. So it's got a broad suite of different contaminants to get a feel for what to expect. And that's what we used to decide for the next few years, what should we be studying in more detail. So study number 1 was really the beginning and was used to design studies numbers 2, 3, 4, and 5. And so it's been helpful, and a lot of people have been using that around the country. So there's another question from Aaron Hansen. Are there any studies underway to look for these priority chemicals in groundwater and drinking water supplies? So certainly there have been studies done in certain areas. I'm not as familiar with groundwater studies, but we've seen some of that work in Wisconsin, and there's been studies elsewhere as well. I would have to look in the literature to give you a little better answer on what the results are, though. Some of them, the dissolved parameters are going to be more likely to show up in groundwater than things like PAHs, which are particle bound. Other questions?
And I think, Steve, I have your contact information up on there, so people can contact you if they have questions after this presentation.
Yeah, absolutely. Feel free to shoot me an email, or you can find me. You can find my information, my phone number on the web as well.
Well, great. That was a very interesting presentation. Thanks so much, Steve. We appreciated this. And everyone have a great day.
I appreciate it.